So today I'll really share with you some of our recent progress on large language model, biomedical large language model specifically. So this is the outline of my today's talk. I'll start with a very brief introduction about generative AI large language model. Then I'll talk about 3 applications we're doing. One is the topic I have been working for over 20 years on information extraction from clinical notes using large language model now. And the second one is really talk about building medical foundation models and how we can use it for medical question answering, medical diagnosis task. And the third one is a new area I'm exploring is actually applying this large language model for literature mining. I'll start the first one, brief introduction to generative AI. I know since ChatGPT, we are talking about AI almost every day, at least for myself within the Yale Department of Biomedical Informatics Data Science. But we all know AI doesn't come out in one day. 1950s research already started looking into AI different aspects, including those foundation works on the a Turing test. And then 1960s, 70s, more application has built primarily based on symbolic and rule-based approach. For example, the ELIZA chatbot, I don't know if anyone played it before, it's still there, out there, you can play it. And also, in the medical domain, we have those medical expert systems like Myson, developed at Stanford University. Then 1990s, we'll look at the machine learning, great algorithm on support vector machine, random forest. I still remember we actually apply all those algorithms for specific tasks in the medical domain. And then 2010, we'll talk about deep learning, RNA, CNN. And I think probably everyone remember the famous example from IBM Watson, right? How it went in the Jeopardy game, but also applied to healthcare problems. Although it's not a successful story, but I think it's really a nice try. And then 2020, more specifically 2022 about ChatGPT, and then everyone talk about generative AI, large language model those days. So I really want to emphasize what are the differences between the new generative AI compared to all the previous AI technology we have been developed, right? So this table kind of try to summarize it. First of all, consider the previous AI. I would argue they are more on analyzing the data, but then the generative AI kind of focus on more converting the task to generation of new content, it could be text, image. And then we found a lot of analysis tasks we can also convert it to a generation task. I'll show an example later on in our NLP extraction. Then the second point, which I think very important, is we used to, I think many of us working on machine learning, deep learning, is we spend a lot of time writing programs to convert the data to machine-readable formats, right? And those days with large language model, you can basically interact with those AI machines using text, using speech. So you don't really need the computational skill to write programs. Average person can actually build something very quickly, utilize those AI models, which to me, I think it's very, very important. I'll show an example in our literature mining, how easy for average user to get information out of those literature using large language model. The third one I talk about, I think the previous machine learning-based system on specific tasks, but now the large language model can show more generalizable or the different tasks. And then the previous model, more relatively small compared now, those models, we're talking about hundreds of billions of parameters, right? And then the last one, the computation requirement also different. Used to be more on CPU, but now it's on huge GPU cluster. I wish everyone bought NVIDIA stocks 2 years ago, so we're all good. We can retire now. And there's a lot of technology behind generative AI, right? But large language model is the key one. And I just give a brief introduction about the history of this whole thing. So you start with large language model, which is developed a long time ago, and it's basically a probabilistic model to estimate the probability of next token, next word, given a sequence of words. That's it, right? And then we move to neural large language model, which actually building the language model using neural networks, RNA, LSTM, which showing good performance, but also facing a lot of challenge about computational inefficiency, things like that. And then transformer come out, which completely address this issue, make it possible to computing large-scale data using the neural network. And then people start working on pre-trained language model. I think many of you remember the BERT model and all those things. So using in an unsupervised fashion, using kind of a large scale of data. But then build on this pre-trained large language model. When people feed more data to those models, they see a tremendous phenomenon about those language models. That's why they call large language model. But there's no clear definition about what so-called large. Personally, I think it might be, has to be like billions of parameters maybe, compared to the previous BERT model, like hundreds of millions of parameters. So the question is like, why suddenly the large language model change everything? Then we have to talk about this emergent phenomenon of large language model. I'm not go details to these figures. Basically, the idea is actually when the model big enough, it not just show the high performance in one task. It actually show very good generalizability on decent performance on all different tasks. Like this diagram showing when the parameter increases, it actually can do all kinds of different things. Suddenly becomes smarter. And build on that, so people actually now, I think almost every day you see a new large language model coming out. And I remember Ben also have a diagram about the landscape of a large language model. But now it's really difficult to keep update with the landscape. But you can kind of classify open source versus closed source or encoder versus decoder technology. And more important now, we're actually moving from this unimodal to multimodal large language model to include text, speech, or even image and all other things. So given that, actually, then there's a lot of application of those large language models in the life science and healthcare, which I don't think I need to go to the details. I just want to, I think everyone agrees there's a lot of application coming out. So then in the next probably 30 minutes, I'll just try to give you 3 applications we're working on. The first one is like information extraction from clinical notes, which I have worked for many years. Like this is the clinical notes from the physician. When they leave the hospital, they write these sign-out notes. As you can see, it's very different from newsletter, right? A lot of abbreviation. It's talk about 70-year-old woman with history of diabetes, mellitus, hypertension, things like that. A lot of details actually in these notes when you try to do a clinical study, medical history, social history, treatment response, all those things, which is not often available in the structured data. That's why we do all kind of NLP to try to extract the information out of those notes. And typically, we're actually doing like 3 different tasks in information extraction from clinical notes. The first task is, you want to recognize the entity. You want to recognize the boundary of a phrase of a disease. In the first example, MRI of the abdominal is a test. June 18, 2008 is a temporal expression. You want to recognize those entities, the type and the boundary. The second one is relation extraction to understand the context of those entities mentioned. So you want to know this June 18, 2008 is a modifier of that MRI entity, right? The relation between those two. The third one is really about we call concept normalization. You find the entity, in this case, this renal cell carcinoma. Then to do some computational application, you have to map this to a concept in medical terminology, which not usually represented as the same term as in the text. So you need to do this kind of mapping. So I think for clinical NLP, maybe 70% of the work is on this clinical information extraction in the last 20 years. And then mainly focus on those 3 tasks. And if you look at the challenges from the clinical NLP, you can see many of them in these 3 areas. Then let's do a quick review, like how clinical NLP research have worked on this task. In about like 90, 95, or 2000-ish, it's mainly rule-based system, like Medley was developed by my PhD advisor, Dr. Carol Furman at Columbia University. MetaMap is by Aaron at the National Library of Medicine. It's mainly rule-based approach, have a dictionary of terms, do the lookup, things like that. And then later on, we kind of move to the machine learning-based approach. Basically, for this task, you actually label each word as the beginning of an entity or intermediate of entity or outside of entity. So you become converted into a sequence labeling task. So you can do a machine learning, okay? And at that time, all we do is a different machine learning algorithm, different feature engineering. Are you using the words, the dictionary, the section, or other representations to improve the performance of the machine learning algorithms? And then 2020, we start to look into more like context embeddings, for example, BERT models, to continuously fine-tune the BERT model on the clinical domains, clinical text, and further improve the performance. This is one study we did on the same task. So this is a table just showing how those different algorithm performance on the same task, which is to extract the medical problem, treatment, and lab test out of the clinical text. That's a challenge on 2010. And then, as you can see at that time, the challenge time, the best performance about 85-ish. We were ranked number 2, about 83. But then when you move all the way from those machine learning to neural network-based approach versus the BERT-based approach, almost improved 5%, which is actually a quite big improvement. Now let's see how large language model is going to change this whole thing when we do this information extraction. So when GPT come out, my first thought is, oh, let me just try this text just to see how it does. So I just gave this task, say, please extracting dose and the frequency information of every drug from the previous notes I showed you. And it extracts everything. Actually, it's pretty good to me. It recognizes all those frequency terms like a BID. If you're not in the medical domain, you probably won't know that's like twice a day, right? All those abbreviations. And I look at this result, I say, geez, this is amazing, because my PhD dissertation is on medical abbreviation disambiguation. And I figured out it's not general. I couldn't develop any generalizable system to really recognize all the abbreviation from Columbia notes, from Vanderbilt notes. And this thing is just like solved it. So I was very impressed there. I said, then I keep thinking like then what we can do, like how this going to change when we do this information extraction. I think two things very important. One is like we probably don't need an individual model. I used to do NER, relation, extraction. Maybe this is a single model can address all those. We're still exploring. But the other thing is maybe you don't need to do label intensive annotation. Now there's a lot of studies showing GPT annotated data can also be used to train models and have good performance. But anyway, we are researchers. We cannot just make a conclusion based on a single example here, right? So then we start a systematic evaluation of this GPT technology on this information extraction. So what we did, the first study is, okay, using the GPT model for the same task to extract the medical problem treatment test out of clinical notes. At that time, we cannot send the true clinical notes to GPT yet because of the security issue. And we made some fake notes and then sent to GPT to test it. So all we did at that time is trying to build a prompt engineering framework, because that's very important for this kind of zero-shot setting. You send something, instruction to the GPT to tell them what you want. You want to make the machine to understand, the AI system to understand what you want. That's why you need a detailed prompt to tell the system what you want, what the output you want. For example, this is some task definition, what I want to extract, and how I want the format to be. And then I also have annotation guideline. What quantifies as a disease entity, okay? All the rules I give it to it. So give more detailed like annotation guideline, things like that. Then we tested its performance on zero shot and few shots. As you can see at that time, the prompt strategy, there's a lot of numbers here. You don't have to look at it. I'll just summarize it. So first finding is you give more detailed instruction to the GPT model. It improves the performance of the entity extraction. Second one is when you compare the GPT zero-shot performance, basically you don't fine-tune any GPT, with the previous, we have fine-tuned, like a supervised bioclinical BERT model. Still, the BERT model performs better than the zero-shot GPT performance, okay? The difference is about the BERT model. If you do exactly matching of the entity, it's 78 versus 59. But if you do relaxing match, means if you find the entity and if the machine identified entity is overlapped with the gold standard, you count it correct, then GPT performance is more reasonable, almost 86. So at this time, we still cannot claim that a GPT is actually zero-shot performance is already better than supervised BERT model. But at least this is zero-shot. You didn't train anything, so it's still very, very impressive. Then we come to, there's a Llama come out, which is open source, right? So then you can do instruction fine-tune. So we did same task, we did instruction fine-tune, and we also want to study the generalizability of this large language-based approach. So we have a data set from 4 different institutions, okay? Mainly using UT physician notes, that's the main training set. And the last one, I2B2 one, is like it never showed up in the training data, okay? It's just as an independent test set. All other 3 data sets have a train and test. So we also did this whole instruction turning task. Basically, like I said, you can converting those, you can make those converting this instruction task to a generation task. Basically, you give the instruction, say, hey, here's the input. The output is generate this HTML text with marked label about entities. So you convert it to a generation task, right? And then you can use those decode-based large language model. And this is the result. So as you can see, for UTP, it's the main, most of the training data is from the UTP, the first one, the first row. So then large language model actually perform similar to the biochemical BERT model because it has a lot of training sets. So the biochemical BERT model still almost similar performance as the large language model. But then for other 2, especially the I2B2, if you look at, this is the data set the supervised model never seen. It's actually showing the Llama model, the large language model, perform better than the supervised BERT model, which is a little bit exciting to us because it's showing more kind of generalizability. Maybe the large language model already encode a lot of knowledge about the medical text. And then what we did next is also, those are on the clinical entity, disease, problem, treatment, right? So the training is really important. But then we are also, like all of us program, it will be also interested to extract non-clinical entity, for example, social determinant of health, which is very important for doing pheno association study. So we're trying to extract all those SDOH factors, like, where the patient was born, does he or she live by himself or herself or with the family, all those things, okay? And clearly, when we compare the BERT model with the Llama model, we show actually Llama model actually perform way better than BERT model. So our guess is actually the Llama model already encode a lot of those more like a general domain knowledge. So when you extract those social determinant information, it's actually extracts a better performance. And just a summary of what I just talked about the previous information extraction task. So far, we're still kind of debating, are we ready to really extract, switch to large language for information extraction? Because the zero-shot performance is still not suboptimal. But with instruction turning, we do show large language was slightly better for some of those, for clinical entity, but much better for like a non-clinical entity. But then you have to consider all other issues, like, because we used to build machine learning-based information extraction system. Then we actually have now a package called a Kiwi to integrate this large language model into a package for our clinical collaborator to use. But then a lot of times, everyone wants to use the latest large language model for this task, okay? But then in terms of reality, they don't have a GPU, okay? Especially if I'm doing Llama 70 billion, you need a robust GPU to load the model. Second, I'm telling you the large language model-based information extraction run very slow. I used to do the deep learning-based approach or machine learning-based, say like a 1 to 2 seconds per node. But here you need 5 to 6 seconds per node using Llama model. And the cost is very high, right? Then if you have millions of nodes to process, so you have to think about the trade-off, I think. So now I switch to the second one. I probably need to speed up a little bit. I don't know how many of you seen this news article about like a 3-year-old boy had all the issues, chronic pain. Mom brought her to see 17 different subspecialty doctors, couldn't figure out what's wrong. She put everything into the ChatGPT, and got the right diagnosis. So we were very interested about this, so maybe this can be used for diagnosis purpose. Then there's actually JAMA papers now start looking at it. They feed the New England Journal of Medicine case report to the GPT to come up with differential diagnosis. The performance is like a differential, top one diagnosis is 39%. Still not optimal, right? So then we think how we can actually to continuously improve the performance of large language model using medical data. For commercial system, you can do retrieval argument, or now GPT also allow you to do some fine tune, but you still have to pay all the money. And then open source one, you have all the weights. We can do continuously pre-train as well as doing fine tune. So that's why we start doing this work. So we start with the open source llama model. We developed this called a Miyama Foundational Biomedical Domain Model. We did both continuous pre-train, start with the open source weight. We prepared 129 billion of clinical tokens with all the literature, guidelines, clinical notes, feed it to continuous pre-train. It requires a lot of computational resource, 200 A100 GPU running for a month. So it's about 100,000 GPU hours. If you charge to Amazon, they charge you $4 per hour. So it might be, it will require like 400,000 just run the 70 billion model. Luckily, we have collaborated at the University of Florida. They have a big cluster, so we are running there for free by collaborating with Dr. John Bian's group. And then we also do fine tune. Once you have this Miyama Foundation model, we prepare a lot of question answering pair to fine tune the model using instruction I showed previously. Then you can also do task-specific fine tune. Now this model finally is actually available in the GitHub, also on the FidoNet, because we use mimic data. So you have to go through, just like you download mimic data, sign the DUA, get HIPAA training, then you can actually download this model. And we actually show it actually compared to, at that time, I have to say, this is based on Llama 2. Now things change so quickly. At that time, when we compare with the open medical large language domain, it show actually good performance on all the different tasks, like question answering, entity recognition, relation extraction, document classification. And then people often ask, like, how do you compare with the GPT? We did compare with GPT on those 8 data sets, which you can send to GPT. If you do zero shot, I'm sure GPT is still the choice, because it's a 100 billion parameter model versus ours largest is 70 billion llama model. And then, but since it's open, you can fine tune, use your own data for the specific task. If you fine tune it, we do show our model actually can outperform GPT on some of those data sets. And now we're actually actively working on converting, improve this model for the medical diagnosis task. Two directions we're working on. One is really high quality data. It's very important. Instead of giving all the data you have, okay, I'll show you next. The other one is that we're actually working on the chain of thoughts prompt. If you ask the large language model to explain why you come up with diagnosis, it actually improves the performance. I don't have a solid result here, so I didn't show, but we do have this result. Compare what kind of data you give the large language model for this task. So we collect a lot of data about, so the input is a summary of a medical case. The output is differential diagnosis. So we go to books, go to all the online, all other people collect the data. We collect all those, like almost 900,000 cases with answers. Okay, that's what we collect from all the different sources. But we notice if we give all those 900 versus we give high quality, which is defined by ChatGPT. So we ask ChatGPT, is this case a high quality case? Give a rate 1 to 5. Rate more than 4, we take it. So we have 440K. But you can see, give 900K versus 440K, high performance one. The last data actually better in the test set of New England Journal of Medicine. That's actually the last 2 columns. That's kind of interesting. And then we actually build a model now, allow you to ask a question that's kind of a chat interface, just like ChatGPT. So you can ask questions, you can give a case report, we give a differential diagnosis, but we have not made it openly accessible yet. I'll explain why. So a little bit discussion about this whole medical board and chatbot issue. I already talked about computational scalability is an issue, right? It's kind of very costly for training those models. Secondly, then in terms of training, you actually now have to think about, are you going to do continuous pre-train, which is like 100,000 hour GPU versus you do fine-tune, it's 1,000 GPU time, which is more affordable. And just to be honest with you, I feel like the change from Llama 2, Llama 3, Llama 3.1 is much more significant than we are continuous pre-train. So now we almost switch to just follow whatever latest model with the instruction fine-tune, which is more efficient, and the performance is also decent. And also there's a reliability of those models. It might give you fake information, I think all you know. But the other last thing is about privacy and bias, which is very important. That's why we didn't actually open our chatbot. Based on our experiment, if I give a prompt which is similar to start with the training data in our training set, it will just output the training data, which is a big risk, especially now we're also considering adding the clinical notes and all those things. So we're still actively working on how we can actually address this issue. Okay, last example. Really think about how we can use this kind of large language model for the information seeking in the biomedical literature domain. So I think you guys probably familiar, you go to PubMed, you type a keyword, it comes up 5,000 articles. I usually just flip 2 pages, then forget about it, right, for the rest. And then I just thought maybe there's a better way we should allow users to actually explore this information. I need an overview of the entire collection, and I can quickly dive into something, ask questions. That's the whole motivation about this project. So this is a platform we built called Bike. So you start with articles title. Right now we work on title abstracts. You go to the large language model using the embeddings, hundreds of dimensions. Then you do dimension reduction to a 2D interface. Each dot is a paper. A similar paper will be classed together. And then on the top, we also build a lot of interactive function. You can quickly select a subsection, ask a question by using GPT, using RAG-based approach, and quickly find the information you want. That's something I want to actually show you. This is showing you, you can actually see different clusters of this visualization. So we now allow you actually say, oh, I have this PubMed query, submit the query, I do the process, I show you this map, how this collection shows different topics. And you can also do trend analysis, basically early papers, how the new paper fill in those blanks. I showed it to some NIH they like it, they want to know what are those blank spaces, because that might be a next IFA type of thing. And we actually now also have an algorithm. If we point to a blank space, we're trying to pop up a text about potential topic for that blank space. Now let me just show you the system we built. So this is a collection we call semantic universe, semantic map. Each dot is a paper. You can zoom in, zoom out easily. And you can see the different cluster. This one is actually the COVID-19 cluster if you show here. Now we can see the trend. You can slide scrolling just to see how the paper pop up. Different color means the paper published in different years. And then you can also do a search. So it's a little bit slow. I'll need to slow down. So you can do a search. I think this is about search. So you can type a keywords. Then we will highlight all the clusters, like COVID-19. You can see the different clusters, the major ones here. But then there's also something else in schedule. You may want to explore what are all those different clusters. Then you can also, we also build a lot of interaction now for selecting a data set to explore the data set. And I'll show you in a minute, I think. Let me just to see. So here, if you zoom in, you see, oh, this is a cluster I'm interested in. So allow you actually to select this collection using this selection tool. In addition to the search you can build. So each selection or search will add to a collection on the right side. So it becomes a sub-collection of your entire universe. And then click a collection, you can see the main topics out of that. What's the main keywords matched in that collection? So if you want to quickly explore what it is. And now we also, if you do, because of the Windows context limitation, we only allow you to select a small subset to then feed to large language for question answering. For example, here I'm typing this is a drug name for the new Eli Lilly's weight loss drug. There's about 10 clinical trial. We select this, then we pop up, you can select any large language model, GPT or even our Milava model. Then you can ask questions about this. Oh, it doesn't show the voice. We have a speech recognition. Basically, it just say, oh, summarize those, select the paper, PMID, the clinical trial number, the phase, the treatment arm of this. Then you come up with a table. So the idea is you can quickly look at this information, you decide, oh, which articles I want to look at it, right? And you can, yeah, the voice doesn't show, but that's the same thing, the same idea. Then the next one is showing, oh, please also add a column about the number of participants for that clinical trial. So then it go there, add a column to the table. It's just like a really conveniently that's why I say, I think the biggest change of those large language is how you can interact with those AI systems now those days. For average person, you don't need to be an AI expert to really do this, right? And then you can ask it to do a summarization. For example, this one is we ask it to summarize the safety report out of that 10 clinical trial papers. And there's actually meta-analysis paper we looked at. Actually, it's pretty decent, the summarization it shows here. Yeah, it actually compare with the other drugs in the same class and generate those kind of conclusion out of the 8 papers. Yeah. Okay, I think I still have a few minutes for questions. So basically, that's the last application. Just a quick take-home message. I think the generative AI technology like large language model is really changing how we do research and development in the medical domain. I wouldn't say, I think at first, a little bit overwhelming, feels like the new AI just address everything, but it's not the case, right? People now find all the issues of, it make a lot of things possible, but then it also bring a lot of other issues we need to carefully evaluate it, okay? And I still keep saying, because we do a lot of application development, the last mile problem, when you're really trying to convert a large language model or AI technology to application to solve a problem, it's still a lot of issue to address the last mile. It's with the large language, it's very easy to build a prototype like the one I show you, but then you're really going to solve something, you still need to spend a lot of time to meet the user's requirement. So just thanks to all our collaborators, foundings, and also happy to take questions. Thanks.
For the information extraction from the EHR, are there like medical specialties where it works better or worse than others? And does it work on genetic data?
Definitely, we see different performances in terms of the disease area, where the nodes coming from. In the social determinism study, we have 4 data sets from 4 hospitals, which is from different specialty. One is the psychiatry nodes. There's actually a lot of SDOH information. And there's one from the UTP, which is outpatient practice, limited SDOH. Then also there's a group from pain related patients. So you do see I used to have a slide just show the distribution of those information in the clinical notes. You will see it's very diverse. Yeah, so that's why the generalizability across different type of nodes, across different institutions is very important.
So question regarding comparing the output that we get from LLM compared to what a physician will do. So let's say you give the large language model a patient and say, go back and pull up all the past medical history and everything and summarize it. are we comparing that to how a physician would personally do it if he goes and then compare it head to head? Because I feel like that's what's lacking in most of the models these days. There is very little comparison.
Yeah. So text summarization of patient medical record is actually one big application of those large language model in the healthcare domain. We have not done much on that, but I saw some papers that actually show pretty good performance. And I participated in a study is more about like give a topic, ask a physician to write an essay about that topic versus like a AI to write an essay about that topic. And with human clinical clinician evaluation actually show very difficult to differentiate between those two. Yeah. I don't have a solid number on the text summarization task to look at the whole medical record. Yeah.
Hi, Dr. Xu. Thank you very much for the presentation. It's very fascinating that your work is. I'm particularly interested in the last demo you're showing. So I have a slight technical questions there. So I saw that you're reducing the dimensionality into 2. Mm-hmm. Is that for the convenience of visualization, or if it is of some other reasons? If you don't restrict to that, would you get more accurate or improve your accuracies?
Yeah. So we reduced to 2 dimensions just for the display purpose. We also have a version recruiting 3D. So you have actually can rotate and all those. So it's mainly for visualization. But actually for example, to identify a topic in the blank space, you may want to go to the original dimension, hundreds of dimensions, to actually look at all those information rather than in the 2D dimension. And also, there's a couple of the algorithm actually converting from hundreds to 2D dimensions is also very important. We used to use the popular Tisney conversion algorithm, but now our collaborator at the University of Michigan, Dr. Qiaozhu Mei, has a algorithm called large-base, which actually I feel it shows better clustering results. So all those algorithms also are very important for this application. Yeah.
Thank you so much.
Hi, that was a great talk. Obviously, a lot of promise in unstructured text and stuff. So my question is more on, as clinicians, we're not just looking at unstructured tests. A lot of it is multimodal data and images and other things. So could you briefly comment on how large language models have changed in their ability to handle multimodal data inputs, or where you see that in the future?
Definitely, like I said, one research direction is multimodal. We're also moving to vision language model now for the melanoma, to adding medical image, for example, text image together to do that. And there's quite a few papers published in those significant journals. For example, pathology. There's also a large language model specific pathology by combining the text and the imaging data and all those things. I think that's definitely a trend. And NIH, if you look at a lot of course multimodal IFAs. Previously, the ODSS has a IFA for multimodal foundational model. So a lot of people applied for that grant.